Finally, we're going to be able to actually do some programming in Blueprint today. We've spent a lot of time in the previous parts, if you've seen those, explaining the engine and how everything works and the systems that make your workflow efficient. Today, we're actually going to implement some actual coding, which is going to be very, very exciting. In this series, we're trying to make a 3D platforming game slash kind of an obstacle course type of game, which is a very good, simple example that allows us to show off a lot of different things. So what I'm going to do for the time being is in the viewport here, I'm just going to delete a lot of these objects over here because we're not actually going to be using most of this. I will, however, keep these around because these will be useful in the next video that we will be doing, which will be talking about collision and physics, because these blue things over here are physics objects. And this leaves us with a nice and empty testing ground for our new actors. So let's make that new actor. First and foremost, we're going to go in here and I'm going to delete the actors that I have already created to show off the actor system. And we'll make a new actor, which is going to be a normal actor, which we'll call BP Sweeper. Opening that up, we are going to do something that we've already done in the previous part. We're going to add a static mesh, or in this case, actually, we can just get away with a simple cube. And then coming over into the transform, make sure that the scale is not locked, because if it is, it will always scale proportional into all directions. We don't want that. What we want is we want to scale this thing in either the X direction or the Y direction. It doesn't really matter which direction we go in. And let's scale this to like 10 times the width. And then in the opposite direction, we're going to scale this to like 0.3. So that's a little bit thinner. And we'll scale it up to being twice as tall. Now we have a nice little wall. And if we add a rotating movement component to this, we can set its rotation rate around the Z-axis, which is the up and down axis, to something a little lower than 180, something like 15. And now, when we put that into the world and we play the game, we can see we have this thing sweeping around. And it's a little bit buggy because of the whole collision situation, which we'll get into a little bit later. And for all that, we didn't need to do any programming. It's literally just adding a couple of components and that's it. So let's do something a tiny bit more complicated before we go ahead and fix the issues with this thing, because that's going to also need a little bit of blueprint programming. For this, we'll make another blueprint class, which is going to be of type actor. And we'll call this BP Pusher, where we'll add another cube and we can set this to, and you see we have it still on not being locked, but this time we actually want a cube. So let's lock it and then set it to being about 10 times the size. Now, if we open up the event graph, we can see we have a onBegin overlap event. We're not going to be using that for the time being. A event begin play, which we're going to be using in a moment here, and an event tick. I mentioned these a little bit before in a different part, but if you haven't seen that one, let me go over it real quick again. Event begin play is an event that will execute a certain script or a piece of your code when the game starts. Or if this object is spawned in after the fact, during runtime, this will just run the moment the actor gets placed or spawned into the world. Event tick will run whatever code is hooked up to it every frame that the game runs. So if the game runs at only 10 frames per second because it's horribly optimized or it's on a bad PC or whatever, this is going to run 10 times in a second. However, if your game runs buttery smooth at like 120 frames per second, this is going to run 120 times in that second. So this is a very useful and powerful event to use, but also one that you need to pay attention to, because if you're like adding a certain score amount to your character every event tick, if you just add one, it's going to be different depending on your frame rate. This delta second pin can help with that, but we'll get to that in a little moment. Next up, we have on the left-hand side here, the variables. This is the cornerstone of programming, a very fundamental, basic thing. If you don't know what variables are, Very easily explained, they are containers for information. I'm sure most of you are familiar with basic algebra. Say instead of calculating something like 2 plus 4 equals 6, we say x plus 4 equals 6. Now we can use this same formula if we want to add anything to 4. So we can just say x is equal to 2. So now we are back at 2 plus 4 equals 6. But if we want to add 10 instead, we simply say x is equal to 10, and now suddenly the same formula without any other interference on our part says 10 plus 4 equals 14. And you can definitely see in programming why that would be useful, because this allows us to build systems that don't have any actual concrete information, but allow us to feed in the information of any specific situation that we might be in, which makes for a very flexible creation of whatever system we want. So if we add a variable over here, we'll see it creates a new var, and it has a type. And this is very important because I said a variable is a container for information, but the variable needs to know what type of information we're going to store inside of it. So by default, it's making a Boolean variable, also known as a bool, and this can only store a binary state. So what does that mean? That means it can only store a 0 or a 1, or in more easy to understand terms, it can store a true or false. So if we compile this right now, we can see we can set a default value to it, and it's a checkbox because it can either be false or true. There's nothing else to put in there, so the engine gives us a checkbox to do that with. And you'll also see that we can change the variable type either on the left-hand side here or on the details panel on the right-hand side. We can also make it a byte, which frankly, not that often used, so I'm not going to go into it right now. We have an integer and integer 64. We'll stick with normal integers for now. Integers are, as you would expect, just integers, which are whole numbers. So that's 1, 2, 3, 4, 5, but not something like 1.5, right? 1.5 is a value in between 1 and 2 that we cannot store in an integer. So let's try that. 1.5, it defaults back to 1, because anything after a decimal place, you can't store that in an integer. An integer can store a value up to billions in the positive or negative. It's not unlimited though. There is a limit to how large the value in your integer can be. It's not an issue that you're likely going to run into because, again, the range goes from, I believe, something like -4 billion something to +4 billion something. But should you need to have a number that is significantly larger than that, that's where the integer 64 comes in. This allows you to store much higher value numbers. It also has a limit, but the chances of you ever reaching that limit are slim to none. Next up, we have a float, which is a floating point number. This is what we use for decimal places. So this, you can see, now has a comma in it. So we can say something like 12.753, and we can put that value with decimal places into this float. Then we've got names, strings, and text. These are all very similar. These store characters, so text. For any practical purposes, these are pretty interchangeable because if you hook them up to a field of one of the other types, the engine will just put in a conversion node automatically in between. So if we go make a string, we can type in this is a test, and you can see it takes in a text. Then we've got a vector, a rotator, and a transform. If we go into a vector and compile that, you will see that this is a much more complicated type of variable already. Because this is not just a float, because we can still put in decimal places, but it's actually got 3 fields here, a x, a y, and a z. And this is where we get into, these variables are called structures, which is more or less just a custom variable that the engine provides you with, or that you could make yourself if you wanted to. And the most basic of that is just the vector, which is a variable that just holds 3 float values and some extra functions and events that you can use to do things with. So if we have a vector, I'll just drag this in, we'll get into the whole event graph in a moment. I can get the vector length, for instance, which is a function that corresponds to the vector type variable or struct. And this puts out a float of simply x plus y plus z. Then we have a rotator, which is very similar to a vector because it also holds 3 different values here. It's just got some different functions on it compared to what a vector has. And rotators, as you might imagine, are usually used to store the rotation of an actor or a component in them. You could store that information largely in a vector as well, but a rotator is designed to hold that information. And then lastly, we have the transform, which if we open that up, should look very familiar. It's got a vector in it because the location is just a vector. Then we've got the rotation, which is a rotator. And we've got the scale, which, as far as I am aware, is another vector. All put together in one type of variable. So you don't have to make a vector for your location and then a rotator for your rotation. If you want to influence those and store those, you can just put them all together in a transform. Those are the most basic versions of a lot of the variables that you're going to be using. Then there's a bunch of different other types as well. We've got enums, which we're not going to get into right now. We've got object types. So these are all of the different objects that exist, which means that we can make a variable, for instance, that is specifically of object type BP sweeper. That can then hold a reference to that object, and they will only be able to hold references to blueprints, to actors that are specifically of the type BP sweeper. If we put any other actor into this as a reference, it won't work and it will remain an empty variable. So any blueprint that you make is also then immediately going to turn into a potential variable type for you to use, which is a very important thing to realize. All that theoretical stuff out of the way, the reason I went over all of that is because we need a variable to store our starting location in. So we're going to make a vector variable here, and we'll call that our start position. Now, back in our event graph, we can drag in our start position variable here, and we can either get the value of it to read it if we need it in a formula or something, or we can set it to write a new value to it. So we can set it to something like 1, 2, 3. And the way we execute that set node is by connecting it up to a event. So at event begin play, this variable will now be set to a value of 1, 2, 3. But we don't actually want it to be set to a specific hard-coded value. We want it to be set to whatever location our actor is located at the start of the game. And for that, we can actually use a pre-existing node. We can right-click to add a new node, and then we can type in whatever we want. So we want to get our actor location. This will pull up a function node that will take in a target and then return a value. And that return value will be the location of the actor. You can put any other actor you want, if you have a variable or a reference to it, into here, and it will then return the value of the location of that other actor. If you don't put anything into it, you can see the default behavior here is self, meaning that this is going to just give us the location of the actor that this is on, which is our BP pusher. If we have 5 BP pusher actors in our scene, each one of those is going to have its own set of variables, and each one of those is going to run this function on its own instance. So I'll just show you that. Putting that in there, we definitely should make the cube a little bit smaller in a moment. If we have 2 of these, this one will run the function getActorLocation and get the location corresponding to this origin point. At the same time, this one will also run that function, but since this is a different actor altogether, it will then return the location of this point instead. So if we set this position now, we can connect it up like that. And now this variable is getting set to the result of whatever this function does whenever we begin play. And the way we can check that is to make this variable public. So if we set this variable to being public, we can then see it in our details panel that we've looked at before. So if we look at this here, we now see our starting position is set to 0, 0, 0 because begin play hasn't run yet. But now if we run the game and we look over at our pushes, this one has a starting position of 2,154, 666 and 0. And then our other pusher over here has a different starting location because it's being put in a different location. Now, we're going to make two more variables, and one of those is also going to be a vector, and that will be called our movement direction, which will also make public. As a matter of fact, we're actually going to make the starting position not public anymore, because public variables usually are variables that we want to be able to influence on a per instance basis. So that means that we want to be able to just click on them and set them in the viewport here. So for instance, this one needs to move in the Y direction. So we set X to 0, Y to 1, and Z to 0. And this one we want to move in the X direction. We set this to 1 and 0, 0. Then we're also going to make a movement speed. And that one is going to be a float variable. When we multiply these two together, which is possible, you can multiply a vector with a float. What that will do is we'll just multiply the value of the float with each of the three, the X, Y, and Z, stored in the vector. We will get a value of a certain direction multiplied by a certain speed that we can use to move these actors around. And that is what we will be doing in event tick. How do we do that? Well, we do that by using the set actor location. And as you can see, by default, the target is set to self. We'll hook it up into the event tick. And here we will use another one of these get actor location nodes because we want to get its current location. And we want to add to that. So we can drag off this and then just simply plus. This gets us one of these math nodes, which allows us to add another vector to it. And the vector that we want to add to it is going to be our movement direction, which we can get, multiplied by our movement speed, which we can also get. We simply multiply those and then add that to our current location. And that we can set as our new location. So if we set our default movement speed to something like 10, we probably want to make that also a public variable because we want to likely influence that on a per instance basis. Now this thing will move in its given direction at its given speed every single frame. It's not exactly what we want, is it? Because we want this to be frame rate independent. That's where delta seconds comes in. Delta seconds is the value in seconds since the last frame ended rendering. So if you're running at 100 frames per second consistently, the delta seconds value will always be 1/100th of a second, so 0.01. If you're running at 50 frames per second, it will be 0.02 because there's been 0.02 seconds passed since the last frame. Since no game almost runs at a very consistent frame time, this delta seconds will probably change from frame to frame. And that is what allows us to make use of it to make things frame rate independent. So if we move this over a little bit, and we multiply our movement speed by those delta seconds, that simply creates a system where our movement is now the same speed independent of what frame rate the game runs at. So let's move these up so that they don't run into the walls because they're going to be only moving in one direction and not back for the time being. And we'll look at this one, right? So this one is going to be moving in the Y direction at a movement speed of probably 100 actually, because multiplying something by delta time makes it move a bunch slower. And as you can see, the one we set to the Y direction is moving in the Y direction, and the one we set to the X direction is moving in the X direction, with a very poor frame rate, which is mostly to do with the facts that I'm recording right now. It also has to do with our project settings, which I'm going to open up real quick, because I have a lumen global illumination set to true, and we don't want that for either illumination or reflection, because that's quite computing intensive. It does look very, very good, but it makes your game run like shit on lower end hardware. And while we're at it, I'm also going to disable the motion blur in here because I don't like the way it looks. And I'm also recording at the same time, so sometimes you will note that if you're working on the engine and you exit play mode, your objects are just gone. And that's because the engine's like, oh, wait a second, your computer actually sucks. Hold on a moment. I'm going to unload some of these objects. When we run the game again, they're going to be there. This is just a optimization thing to stop the engine from being so sluggish. So what you can do, you can select them and you can just pin them. That will always force them to be loaded if that's specifically something you're working on at the moment, which for these 3 objects, we are. Now, these blocks are moving and we're doing that through our own made code. So if that's working so far for you, give yourself a pat on the back because you've just made your first script. It's honestly that easy. But it's not very usable right now, right? Because we probably want these to be moving back and forward. And there's a bunch of ways we could be doing that. But for the sake of making things stay simple, we're going to be adding 2 more variables and doing a little bit of simple math. It's the most educational way to do it anyway. So we're going to be making a max move distance variable, and we're going to be making a is moving back, which that one will be a bool. You will also note that if you use this specific capitalization technique, where you capitalize the first letter of every new word, the engine will actually separate those into separate words in your details panel so that it's a little bit more readable, because you can't have spaces in your variable names. Now, what we're going to do here is after we set our actor location, we're going to check if the new actor location is more than our max move distance away from the original location. There's a number of different ways of doing this, but the easiest way to do that would be getting our actor location and getting our starting position. You can just hold Control, by the way, and drag these into the event graph to immediately get a getting node for them. And if you do the same thing holding Alt, you immediately get a setting node for them. You'll be seeing me doing that a lot. So if you're wondering how that actually works, that's how you do it. And if you drag off a vector, we can use the distance function on it, which lets you plug in 2 vectors and returns a float. And that float will be the distance between those 2 vectors. So if our starting position is 0, 0, 0, and our actor location has become 0, 100, 0, the distance will be 100. Now, that becomes exponentially more complicated when you're moving into more than one direction. And this function just calculates all that for you, which is very, very nice. And then we simply want to check that against our maximum move distance. Have we moved more? Is this distance more than we should be allowed to move? And there we can just simply check, is this greater than that? This would simply check top value being greater than the bottom value and output that in the form of a bool value, just like our Boolean variables have been so far. And that's the basics, the beginnings of building logic in Blueprint as well, which we will probably get into a little bit later at some point. If we hold down the B key for branch and click, we just immediately add a branching node, which takes in a bool, and when that bool is true, it will execute whatever we put into there, and when that bool is set to false, we execute whatever is set to there. We can put in a variable there if we want to, which we're going to do in a moment. But for now, we're going to put in the output of this little calculation that we've done here. Because if that distance is indeed greater than our maximum move distance, we want to start moving back. So we set our is moving back to being true. But that's going to be an issue, isn't it, actually? Because, well, that's a bit of an issue because we want to set it back to being false again when we get back to our starting position. So what we'll actually do is we'll drag in a reference to our current value for is moving back, and we'll simply type in not. This will just take in a bool and output the opposite value of whatever it is. So all this is doing is saying take our is moving back, invert it, and set that as its new value. And if this is false, we won't be doing anything. Now, in order to make the moving back itself work, we're going to put in a branch node here as well. Because if we are moving back, we want to move into this direction, but in the negative direction of that. So as long as this is false, we are not moving back, we're moving forward, all of this still applies. But if we are moving back, we want to create a second set actor location. We want to do all of this, but we want to multiply this by -1. Issue being is that this is 3 values and we just want to multiply it by 1 value. So we can right click this bottom pin, convert the pin to a float, either single or double precision, it doesn't really matter. And then the bottom pin becomes 1. And we're going to be multiplying it by -1 to invert it. So all the positive values will become negative value and all the negative values will become positive values. Using that, we will be moving in the opposite direction now. And after that, we can hook this up into the same branch node, and that works perfectly fine like that. And then all we have to do is, after we set the is moving back, we're also going to set our start position back to being our current position. So we'll get the actor location. So that way, when we start moving back, it's comparing with this little code here. It's comparing against the location where we were at when we went back. Now, there is a couple of minor issues to this code which are going to be difficult to show off. But before we do any of that, let's actually check whether what we've made works or not. So I'm going to select this one over here, and I'm actually going to delete this other one because we're not going to be using it. We want to make sure that our max move distance is actually a public variable so that we can change it. And let's set that to 500. So after 500 units of movement, it should go the other direction again. And again, since I'm recording, my PC doesn't really like it. This is very low frame rate. And that didn't really work, did it? And the reason that didn't work is because we put the -1 multiplication a little too late into the chain. What we should be doing is we should be getting the actor location and making a extra plus here and hooking that up this way. So what we'll be doing is, hopefully this makes a certain amount of sense to all of you. What we did before was we got our new location and then multiplied by -1, meaning that it's going to teleport to an entirely different location. What we want to multiply by -1 is just the offsets. And then we add that to the current actor location, and that is the proper code that we want. As you can see, it's always important to keep testing whatever you're making and not just make everything and assume that it works, because a very small little mistake can easily slip into your work. And now, after all that, we can see that it's working. It's going back and forth, 500 units one direction, 500 units into the other direction. Now, there is a tiny issue, that being that over time this thing will start drifting to either the left or the right side. On average, that should cancel out and it should remain in roughly the same place. But on average and should maybe, those aren't really words that you really want to get used to using as a programmer. So we want to make our system as solid as possible so that it doesn't actually do that. Because right now, we're just setting the actor location and it can very well overshoot our maximum move distance. And then that becomes the new starting position to calculate its move distance. And if it just every single time overshoots by 3 units on the right and only by 1 unit on the left, every cycle is going to be 2 more units to the right. That's very much a possibility that could happen over time. So what we'll do instead is, when our distance check here ends up being true, what we do is we manually set the actor location again. So we set the actor location to being our starting position, which we can just copy and paste. And to that, we will add our maximum move distance multiplied by our movement direction. And this way it will always exactly be set to its maximum movement distance when it reaches even just a unit or two beyond that distance. Now, here we have the same issue that we had before. I'm just trying to get all these nodes into a somewhat readable place, by the way, where we actually need to put in a branch to check whether or not we're moving forward or backward to multiply this value by -1 or not. And here we start getting into, okay, we're doing the same thing a number of times, which is less than ideal. That's not good programming practice. So what we'll do instead is we'll make something in form of a variable that can do that for us. So we'll make a, let's call it invert float, something like that. Obviously, there's going to be a float value, which by default we'll set to a value of 1. Then we can delete this second set actor to location in our branch here. We can actually remove this branch altogether, and we can simply multiply this instead of by -1 by our invert float, which is a bad name for the variable, because when this is 1, that means that it'll be moving forward, and when this is -1, it will be moving backward. And now we suddenly don't need a branch, we just need to update the value of this thing, which we can simply do in the same way that we updated the value of our bool here at the very end, which is getting a reference to it, setting it, and simply getting a reference to it and multiplying that by -1. Meaning that if this is set to 1, it's going to be set to -1. And if it's set to -1, negative multiplied by negative becomes a positive number. It'll become 1. And now we can get this and multiply that by our invert float to create the offset in either the positive or negative direction from its starting position. And this will now, number one, make our code a little cleaner to read because we don't have a bunch of branch nodes all over the place, which is always nice. It makes it easier to eventually compartmentalize this code into different functions if you would want to. And it's just generally better practice to do so. So now this should work fantastically. You're not going to be able to see much of a difference here when we run the game because, again, this is very much something that would drift out of space in a long time. So while we might not see a exact difference in behavior right away, we've just improved our code by quite a bit, from being functional but maybe a little iffy to actually being quite solid and workable. And I think that will be plenty enough for today's video. It's been quite a long one, but it's very important that you understand the basics of what we have done here today, adding all these nodes together and doing the math that we did. Even if you don't understand every single step that we've gone through, feel free to watch through the video again a second time and try to understand the things that you might have missed out on, and at least get a general feeling of what we did and why we did it. Next time we're going to go into a little deeper with more blueprint stuff, and we're going to fix that issue that we saw at the start of the video, which is also going to be present with this pushing block, actually. And that is the glitchiness that happened when we ran into them, which, yes, the frame rate for this is really low at the moment, because again, my PC is not a fan of rendering this while I'm also recording. But you can see this glitchiness, that's no good, right? And that's got to do with some collision. So we're going to expand the blueprint there to do things regarding its collision. And we're going to talk more generally about collision itself. And a very big thank you to all of my Patreons. You can see them on screen right now. If you want to help out supporting the channel, there's a link down below in the description to the Patreon page.